So we've covered the idea that lenses have foci, technically speaking, thin spherical lenses, which means that either the one or both sides is convex or concave. So if they've got mixed sides, they're so-called meniscus lenses. And these are icons, so these are basically like the equivalent in optics of something like a resistor diagram or a capacitor diagram in electricity and magnetism in circuits. So don't take these too seriously. What we need to have be the case is these are thin. So they're thin compared to the radius of curvature. So this is what an actual thin biconcave lens would look like. You'll notice it's pretty thin. And this would be a not so thin biconvex lens. Actually, this is terrible, and this will display something that we'll talk about called spherical aberration when we get to the end of the chapter. But for now, just think about these as icons. And it turns out that meniscus lenses can be just thrown into these as either converging or diverging, depending on the relationship in between the object and the focus. So for now, we'll go back and do the thin lens equation later. But what we have is the lenses we'll talk about, thin spherical lenses, have a focus, which means they'll create coherent images. And that we'll use one of these icons, this if it's converging and this is if it's diverging. So the first thing that distinguishes, or is a little bit different in between lenses and mirrors, is the fact that it's kind of unclear where we should put the focus. In fact, maybe they don't have a focus. They have two. For a mirror, like a concave mirror, it's clear that I should put the focus on the shiny side. And for a convex mirror, I should put the focus on the non-shiny side. But what about this? So it turns out that the focus is determined for a lens based on where the light is coming from. And it can be either on the left side or the right side without me flipping the lens. So just as a quick reminder of what a focus is in the first place, and let's have the light coming in from the right. So let's put in some light rays. Okay, 6 is overkill, but I'm a symmetry freak, so there it is. So I've got some light rays coming in parallel to the principal axis, aka light rays from infinity. And this is what we went through last time. The Snell's law argument is that this gets bent down once, twice. Should do this right. Once, twice, and then once, twice. And all of these should go through the same point, aka the focus. Okay? Imagine that the light came from this side, and that's totally fine. A lens is transparent. It doesn't have a preferred side. The focus would be on this side. So the takeaway from that is put the focus where you need it. So it actually could have a focus on either side. And that's true for converging or diverging lenses. So keep that in the back of your mind when we're figuring out our rays. So now what we want to do is basically mirror the analysis that we did for mirrors and do ray diagrams and then an equation that gives us precise numerical descriptions of where images show up and their heights, etc. So ray diagrams and the thin mirror equation. Well, we'll just call this ray diagrams because we'll do this one at a time. And the point of a ray diagram is that it's a really nice qualitative tool. You can get kind of quantitative with it. And we'll do a converging lens first that will give you the basic properties of the image and make sure that you haven't gone completely off the rails when you're actually doing the numerical analysis. So let's take this converging lens and let's put a nice object here. And this is always true. D naught, positive number, that's the object. So this is actually going to be positive. It's going to not define everything as positive like it did with mirrors, but just like mirrors, the object distance is always positive. And we've got light coming in from this side. So first question is, where shall I put my focus? Yes, so light coming in from this side, I should put my focus on this side. And just so we have something to do, some location, I'll put it here, wherever. Okay. And now what I want to do is I would like to come up with 3 rays that are really useful in, one, deriving the equation that we'll semi-derive, and 2 is helping me draw some diagrams that would locate this image. So ray 1 remember we need 3 rays. 2 rays will always converge somewhere as long as they're not parallel. So we technically need 3 rays to define an image. So ray 1 will be the easy one, the one that basically the focus gives us for, free. Is if I come in parallel off of this object, I will go out through the focus. So in parallel to the principal axis, out through focus. Okay. Ray 2 is going to have the same sort of rationale behind it, but if you tried to take what we did with mirrors very literally, you'd realize that it doesn't quite work. And the thing that you should have in the back of your head when you're doing these is that this is a converging lens, right? And likewise for a diverging lens is a diverging lens. So if you ever draw a ray that is diverging on a converging lens or converging on a diverging lens, you know that you've made a terrible mistake. So I'll draw a naughty ray. So here's a ray that looks like it's going towards the focus, and then it comes out parallel, right? Because I know that I should flip the parallel and focus rays. That's how I get ray 2 from ray 1. This doesn't look good to me. This is a diverging ray on a converging lens. So it turns out that we can still do the focus parallel thing. We just have to think a little bit more carefully about how to do it. So remember this discussion, and lens has a focal point on either side. So remember what we're doing is we're essentially thinking about flipping the arrows on ray 1 to get ray 2 in some sense. And what I know is that I'm going to come out parallel. So if I come out parallel on this side, imagine instead of coming out parallel, I went in parallel. Where would I go? I would go through the focus here, right? Same distance away, but on the other side. So it's still, it's not technically the focus in the sense that, the rays coming from infinity won't go through it, but it's the point located at that focal length. So I just put it in parentheses. And if that was a little bit wordy, then I'll just draw this ray and you'll be like, oh, that makes sense. So I go through the focus and I go out parallel. Literally just think about flipping the arrows on this ray. So if I went in parallel coming from the right, I would go through the left focus. Just like if I go in parallel from the left, I go through the right focus. This is a good ray. So what I want is in through same side focus. Out parallel to the principal axis. And then ray 3 was hit the center. It still hit the center. But because this is a lens, and don't let the cartoon or icon guide any of your decisions. Like really, this should be super thin. So I want to hit the center. What that means is like right there. So I'll come in and hit the center. What's going to happen to this? Well, I mean, in real life it's going to refract. But the short argument for what happens is that if I really look closely at this part of the lens, I've got, I'm a little bit above the principal axis, so I'm curved this way. And here where I leave, I'm a little bit below the principal axis, so I'm going to be curved that way. So effectively what happens is if I zoom way, way in on this, I'm going to have what's effectively 2 parallel sides. And if I have a ray coming into 2 parallel sides, it'll kink. But as you guys probably noticed when you were doing your first lab at home, with even Tupperware containers that have a rounded side, is that this angle and this angle are the same. All that happens is it kinks. So the other really important way of realizing that parallel sides on, for instance, glass, they don't actually bend the ray, they just might kink it by a tiny amount, determined by how thick the glass is there's no significant refraction when you're looking through your front windshield when you're driving. That would be a pretty bad situation to be in. So if I have 2 parallel sides like your front windshield, all it's going to do is slightly kink the ray. So effectively for a thin lens, I can literally just go straight through in a straight line. And the other reason I know that that's the case is it gives me exactly what I want. So hit the center straight through. And now we've got 3 rays, and they all seem to converge, and they give me what appears to be a real, because the light rays actually converge there, and inverted because it's underneath the principal axis. In this case, it's a real inverted image. Okay, so that's ray diagram for a converging lens. So really quickly, we'll do diverging. I think this would be a great opportunity, of course, for you to pause and figure it out yourself. And really the big trick is the location of the foci and realizing that, honestly, you kind of have 2. So, of course, right now you're scrambling for the pause button to make sure that you don't get the answer, just kind of hand-delivered for you. But I'll do this pretty quickly. I'll just draw it up there. And we'll be uncreative. We'll come in from the left again. So I've got a diverging lens now. And I've got an object. Put the object here. Okay, I've got light coming in from the left-hand side. Where is my actual focus? Well, so my actual focus is here. And I'm pretty sure I'm going to need this secondary opposite side focus because I kind of know how this is going to play out. So I'll put that there just, right from the get-go. Okay, ray 1 is going to be in parallel. And what in parallel means is in parallel to the principal axis. Okay, and I know it's going to go out focus. What does that mean? Well, it can't go through this focus, can't actually go out through this focus, because that's a diverging lens doing converging things. So it's out as if it came from this focus. So if I dot, 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 dot from here, I've got a ray that looks like this. This looks like a diverging lens ray. It does have a relationship in between parallel and focus. This is what we did in the last video, kind of qualitatively. So we saw that this thing should have 2 refractions away from normal because of its concave geometry. So in parallel to the principal axis, out as if it came from focus. What about ray 2? Similar to that, all I know is that I want it to come out parallel. So what could I do to make this thing come out parallel? So I've got to have a diverging lens. This thing, if it's, if for instance it comes in up here, it's got to bend upwards. So it turns out this will let us do that. If I draw ray 2 coming in towards this focus, the opposite side focus, and it comes out parallel, then I've got what I want. So again, the other way of thinking about this is flip the arrows. I have a ray coming in from the right-hand side, parallel. It's going to go out as if it came from the same side focus, flipping the idea of this. So what we'll do is we'll call that in towards opposite side focus. Out parallel. And be somewhat pedantic, out parallel to principal axis. Okay. I think literally of having graded many, many geometric optics exam problems, I think this is the trickiest ray out of all of them, mirrors and lenses included. You know what's not the trickiest ray though? Ray 3. So same argument, we don't care about the curvature of this. Basically, a little bit above, a little bit below, the 2 sides are parallel. They might look like that now. Let's just go straight through. And we'll even cheat and just say straight through center. Final sanity check. This is a diverging lens and it's doing diverging things. Okay? So drink in that ray diagram, and then what I'll do is, so this will create a coherent image. It's got a focus, we know that. Where is that coherent image? It's going to be virtual, and I'm going to find it by tracing these back. And maybe it's because the quarter is wearing on a little bit, and I'm getting better at drawing these, but kind of remarkable that it actually works like this. So this would be an upright virtual image. The rays don't actually converge there. I have to trace them back, and they appear to have converged there at some point in the past. So these are ray diagrams for thin spherical mirrors. So what I'm going to do, because they're up here, is I'm going to actually just split this into two, and I will show how you would use a couple of these rays to prove the mirror equation, and then put up the sign conventions. And then we'll use the mirror equation a couple of times and do one or two problems. So let me just pick on these two rays. So let's, again, we're not going through the full proof. I just want to sketch the essential geometry because the geometry is important. So we'll call this proving the thin mirror equation. Thin lens equation, what are we doing? And just one of these is a little bit more than we need. So let me just take, top guy. So we've got a couple of things you can already start seeing. Similar triangles and similar triangles, of course, will be how we prove this. So this is d naught, this is di. This is the height of the image, h0, or h naught, and this is the height of the object, h naught, and height of the image, hi. Getting ahead of myself. And as you can see from ray 3, which goes straight through, this angle and this angle are the same. So ta-da, I have a couple of similar triangles. And the similar triangles, at least in magnitude, obey the following relationship. H naught over hi is di over d naught. And I'm going to throw some absolute value bars on things because we don't know the signs of these. Okay, so that's from the similar triangles. The next set of similar triangles, what I could do is I could express them in terms of this f. And they're going to look pretty familiar. So also hi over h naught. So I've got a triangle that, again, has this height. If you look at the second ray, I can express this in terms of hi and that in terms of h naught, except the distances are a little bit different. So it's not all the way to the image, it's di minus f. So di minus f, so this is the one I care about now, right? And f. So these two little triangles. Yeah, we're getting cluttered, but we'll just say this. This is the ray 3 triangle, and this is the ray 2 triangle, and they're literally the exact same triangles that we used and mathematical relationships that we used to get the mirror equation. So these things together with some algebra, and feel free to work it out if you want to, but the important part is this, is that they can be rearranged to get the exact same equation that we saw before. So one collection of mathematical symbols, two names. Okay. The thing that was sleight of handy is at some point I dropped the absolute value signs, and the absolute value signs need to be replaced with SIGN signs manually, so we'll do that. And this is going to be true for all mirrors. And I have a mnemonic. I think the general thing that textbooks do is they just kind of tell you, dude, you better remember this stuff. So we'll just say, if you're using this, you better do this. So, D naught, positive, always. Easy one. F is positive for converging, and F is negative for diverging lenses. DI is positive if it's on the far side from the object. So the way that you kind of remember this is the default behavior of a lens, because it's transparent, you think that light goes through it. And so if the rays themselves are actually obeying the default behavior, then what you say is that's positive, right? So anything that makes it through either F or I, if it's on the opposite side as the object, we call that positive. And if D naught is negative, then that would be the same side as the object. Okay. So for this picture, which is really gross, so I'll quickly sketch it again down here. So what we had is a converging lens, and this is the object, and it made an image over here. So the sign conventions for this would be object is positive, that's free, that's always true. And then everything else is on the far side. So we kind of expect that things make it through lenses, and if they made it through the lens, then that's positive. So in fact, both the image and the focus are positive for this scenario. Okay, the second one that we sketched pretty quickly with the ray diagram was this. So we had an object on this side, we had a focal length on this side, what am I doing? And then we created a virtual image which was upright on this side. So always, always, always the object is positive, it defines positive, but because these two things didn't make it through the lens, and you kind of expect things to make it through the lens, this is negative and that is negative. So in fact, both F and DI in this case are negative. Right? So again, one way of doing this is just memorize the chart of sign conventions. The other way of dealing with this is to kind of remember that somebody says lens, you kind of expect like, oh, light makes it through lenses. If the light makes it through lenses, the focus and the image, then you call that positive. And if it doesn't and you end up with stuff on the same side, that's negative. So whichever works for you, just make sure that you get that down. All right. So we'll do a couple of problems, and then after that, I think lens maker's equation, and yeah, and then optical instruments will be next week.